Okay. All right. For those of you just joining or watching on the video, your exam scores have been posted. And if you have any questions, you want to see your exam, just come to office hours, and I'm happy to let you see your exam. I'm happy to answer any questions you have. But I do keep the exams, so we'll have that. Okay, I want to revisit this topic of rejection sampling. We introduced it last week on Friday, but it is important enough that we'll take another look at it. The scenarios in which we use rejection sampling, are a little bit limited. You have to be in a situation where we have the PDF available, but we don't have the CDF or the inverse CDF available. So there's not going to be a ton of situations like that. A lot of times you will be able to either figure out the CDF or the inverse CDF. But if there's a situation where you can't get the CDF or the inverse CDF, then you can use rejection sampling. You can also use it in higher dimensional settings. In higher dimensional settings, we run into other problems, and so we have other methods that we will see later, like the Gibbs sampler. But rejection sampling can be generalized to higher dimensional settings as well, especially if you have a kind of a multivariate distribution that is semi-similar to the your target distribution. Then rejection sampling in a higher dimensional setting can also work. The way the algorithm works is that we have some kind of PDF F, but we're not able to generate random values directly from F. And so the goal here is to get a random sample of values, a sample of random values that look like they come from F. And so what we will do with rejection sampling is that we are going to generate random values from a distribution that we can generate from. And so we'll generate values from a distribution G, okay, just some arbitrary distribution. The requirement is that the support of F is fully contained inside the support of G. And you can see why that would be a requirement, especially for something like rejection sampling, because if you want a random sample drawn from F and this requirement is not met, then that means there's going to be areas of G where the probability of generating that value is 0, but there's areas of F where the probability is not 0. So it just means you'll just never generate certain values of F if this condition is not met. Okay, so like for example, let's say your target distribution is the normal distribution. The support of the normal distribution is technically negative infinity to positive infinity. And let's say you decide you're going to generate random values from the uniform distribution, okay? And you might go to say like -6 to +6, okay? And -6 to +6 will cover like almost 100%. However, is it theoretically possible that a normal distribution generates a value at say 6.5 or 7? It is theoretically possible. It's very rare. It's like a 1 in a billion chance, but it does happen, and that uniform distribution will never create a value. Will never generate a value, outside of the range that you specify. So you could say, well, okay, well then, what if I go out to my uniform to +7 or -7? There's always going to be some kind of compromise where, it might be like a 1 in a trillion situation, and you can just say, well, okay, for all intents and purposes, we don't have to worry about it. But if you want to have a random sample that truly reflects F, then the support of F must be fully contained within the support of G. Okay. And the other thing is that you need to have some constant value m, a non-infinite constant, okay, such that when you multiply m times g, it will be greater than or equal to f for all of the values there, okay? And then the most efficient choice of m in this case is going to be whatever f divided by g is, the maximum value of that quantity, okay? And that way, you know, whatever the largest value of f divided by g is, if you multiply g by that quantity, then you could see that that this condition will be true, that m times g will be greater than or equal to f, okay, throughout the whole thing, and it's not going to be like any larger than that, okay? Otherwise it will be, you'll have kind of like a wasted space there, okay? All right, and so the way it works is we're gonna just go ahead and generate a value from G. We calculate something, we'll call this the acceptance ratio, this R function, where we take the PDF of F, we divide it by M times the PDF of G, okay? And so because M times G is all greater than or equal to F for all values, this ratio is always going to be 1 or less, something between 0 and 1. And now we generate a random uniform value between 0 and 1, and that will determine whether we accept or reject that value. So if this rejection ratio is, say, 90%, we will accept it 90% of the time. If this rejection ratio is, say, 0.02, okay, or acceptance ratio is 0.02, then we're only going to accept 2% of those values, okay? And we just repeat this over and over and over again, and eventually, after you generate a bunch of values from G and you throw some of them away according to this process, then what the values that remain will come from the distribution of F. So an example that we looked at is the folded normal. Actually, the first example that we covered last week is the beta distribution. Let me, I have animations to go with each of these things. So let me actually pull up last week's. Okay, so for the beta distribution, our target distribution that we want to generate from will be the beta 2,2 distribution, okay, which looks like this upside down parabola. The proposal distribution G is going to be the uniform distribution, okay, and what we're going to do is we're going to multiply this uniform PDF, which is just 1, times basically a constant, so that the constant times the PDF is going to be greater than or equal to G of X everywhere, okay? So, so we're going to multiply it by 1.5, and this is the result, okay? So now we just have this kind of rectangle, and we're going to generate values from the rectangle and accept only some of these values. So let me play this animation here. Okay. So I'm going to go kind of one frame at a time, and the code for this animation is also posted on Canvas under the week 4 module. These rejection sampler, folded normal, rejection sampler, beta distribution. These R scripts will load up a package animation and work here. Actually, I think it might be worth just running through the code here. Okay, so we have 2 functions. These are both PDFs. Okay, so we have the PDF of F, all right, which is going to be the PDF of the beta distribution with shape parameters 2, 2, and then the PDF of G, which is going to be the uniform distribution. And so DUnif is just going to output 1 no matter what I do. Okay, so whatever I plug into G, okay. What's going on here? It's always going to output 1 unless I put in a value. Unless I put in a value greater than say the PDF there is going to be 0, or if I put in a negative value. Okay, so anything outside of that range from 0 to 1, okay, the PDF is 0, but anything between 0 and 1, the PDF is 1. Okay, so that's just that. G times M is going to be this. Okay, and so I'm going to start off with a plot of the normal density here. Okay, or not normal density, the beta distribution density. Okay, in red, and then this is going to be kind of our proposal value. And in the animation, okay, sorry, I'm having computer problems here. I'm going to run this loop, okay, and within the loop, with each iteration, I'm going to draw a vertical line to show you the value that I'm going to propose, okay? And that shows here. So we propose a value between 0 and 1 according to the uniform distribution. So all values between 0 and 1 will show up with equal probability. Okay, and then now we calculate basically the acceptance ratio, which is going to be at the top would be 1, at the bottom would be 0. Okay, and we're going to pick some kind of just basically where the line crosses the density. That's going to be the acceptance ratio, because we're going to do the PDF of F divided by M times G. Okay, so the blue line represents N times G, and so when the red line and the blue line touch, that's going to have an acceptance ratio of 1. And down here, when F is 0, the acceptance ratio is 0. Okay, and so right around here, I don't know what the acceptance ratio is. It's like 80% of the way. If it's like halfway right here, acceptance ratio would be like 0.5. And we're going to generate a random value of U. Okay, 0 is down here, 1 is up here. Okay, so this random value of U is right here. It's below the red line. Okay, so we will accept it. Okay, so when we accept it, we're going to put in I'm going to color that dot green. Okay, to show that it was accepted. And then we're going to propose another value. Okay, so here I propose a value over here. Just again, random uniform between 0 and 1. So we're proposing something like 0.58. I'm going to generate a random U. Okay, most of these values will get accepted. U has to be something like 0.99 for it to be rejected. Otherwise, 98% or whatever will get accepted. Here, the random value, even though it was like 0.9, okay, it's still under the red line, so we're still going to accept it. Okay, so we accept it. It gets colored in as green. And then we move on. Here I propose another value. I'm proposing like 0.2. This time, the random U I generate, okay, it's similar to the random value over here. It's 0.9 something, okay, but it's above the red line. So this value is going to get rejected, okay? So it's not going to get accepted. And so I'm going to color that dot in as red. Now, just to kind of show that it was something that was generated, I'm going to just leave a little red dot there. Okay, so we have a record of something. Okay, over here we're proposing a value of, say, like 0.95. Okay, close to 1. The beta distribution rarely generates values close to 0.95. We'll generate a random value of u. Okay, it's above the red line, so we reject it. Okay, here we propose another value around 0.62. We generate a random u here. It gets accepted. Okay, we propose a value near 0.2 again. This time, the random u that got generated is down here, so we're going to accept it. Okay, and I'll just go ahead and run the animation. And so here you can see the black line showing what values we're proposing. It proposes values between 0 and 1 with equal probability, and it's just generating random u's. Sometimes the random u is below the line in which we would accept it. Sometimes it's above the line in which we would reject it. Okay, this one came really close, but it was below the line. This one came really close, it was above the line. And so the exact kind of ratio that we would end up accepting, okay, is going to be follow the distribution f. Okay, so you can just see this: propose, sample a random u, and then accept or reject. So it's going really fast, but it says propose, sample, accept, propose, sample, reject, propose, sample, accept, propose, sample, reject. And so it's just kind of going through over and over. And basically, this is what your computer is doing really quickly, or perhaps in a vectorized form, where it just proposes a whole bunch of values. It calculates the acceptance or rejection ratio for each of these things, and it either accepts or rejects some of them. And so you can see anytime it proposed a value near 0 or a value near 1, almost all of those values got rejected. Oops. So this is kind of the last image here. You could see values that over here that were proposed got rejected in red. Values over here that got proposed got rejected in red, and values underneath the curve are in black to show that they were accepted. And that's what we have going on there. Folded normal, we're doing something very similar, except this time our proposal distribution is going to be the exponential distribution. Okay, and so the exponential distribution is going to propose values closer to 0 a lot more frequently, and it can technically propose values as high as positive infinity, but the probability of proposing values as you get higher and higher gets lower and lower. Okay, so the PDF of the folded normal is shown in red, and the PDF of the exponential is shown in orange. Okay, the PDF right now of the folded normal is there's locations of it which are higher than the PDF of the exponential distribution. So what we need to do is we need to scale up the PDF of the exponential distribution by some factor so that it is greater than or equal to the PDF of the folded normal distribution at all locations. So we can do some math. We do some math and we figure out this is the value that we should scale by, which is around 1.32. Okay, and so if we do that, then the PDF of the proposal distribution, the exponential times our constant m, okay, is going to be greater than or equal to the PDF of the folded normal distribution everywhere. Okay, and so again, I have an animation to illustrate this. You know what? Let me give you a view quiz answer. Hold on. All right, sorry, it's loading. Week 4 Wednesday. Okay, so here's the exponential distribution shown in blue. And it's a little bit difficult to illustrate this or show this, okay? But the black line is values that are going to be proposed by the exponential distribution. And as you watch, what you'll see is that values closer to 0, the black line is going to show up more frequently around, closer to between 0 and 1. And on occasion, it will show up, between 2, 3, and 4. But less so, okay? So most of the time, this black line will propose values between 0 and 1. Sometimes it will propose values greater than 2, but less often. It's a little bit hard to kind of illustrate how often these values are being proposed, okay? But here it proposes a value like, I don't know, 0.8 or something. The acceptance ratio there is, close to 100%, okay? So now you have to kind of recall that 100%, if U is 1, it's at the top of the blue line. So over here, if the random U that gets generated is 1, it's going to be at the blue line. The random U that gets generated 0 will be at the bottom, okay? And so the acceptance ratio here is close to 0%. Here it's around, 50%, okay, where the blue, red line is halfway between the blue line and the x-axis, okay? And so anyway, we'll look at this. So this value gets accepted. I'm going to propose a new value. Again, exponential proposes values closer to 0 quite frequently. I don't know what the acceptance ratio is there. But here, the random U that it generates is 0.9 something, okay, close to the black line or blue line, so it gets rejected. So a little red dot to kind of keep track. Here it's proposing a value near 2, okay, and it's kind of a toss-up whether it's going to get accepted or rejected. Here the random U that it proposed is above the red line, okay, so it's going to get rejected, okay. Here we're proposing a value of around 0.4, okay, and the U that we proposed is close to 0, so this one is far below the red line. It's going to get accepted, and we just kind of let it run. So again, here we're proposing a value near 2 again. This time the random U that I generate is below the red line, so it's going to get accepted, okay. And so we can see anytime we propose a value near 2, there's around a 50%-ish probability that it will either get accepted or rejected, depending just on the random U that I generate here. So I'll go ahead and just let this animation run again, and it proposes. So here, it proposed a value all the way out 4, but it got rejected. It proposed a value, out here that got rejected, and you can see most of the time, this black line is proposing values between 0 and 1. Okay, and that's just the nature of the exponential distribution, okay? On occasion, it will propose a value greater than 2, but not very frequently, okay? So most of the time, the black line is proposing values over here, sometimes in between here and here, and on rare occasion, it will propose a value, greater than 3, okay? But quite rarely. So it's still running, but I think you guys get the picture. Oops. And so, after letting it run for some iterations, I think this is a couple hundred iterations. These are the black dots reflect what gets accepted, and we can see that it follows the target PDF of the folded normal distribution, which is what we want. These red dots get thrown away, so even though they got proposed according to the exponential distribution, we don't accept them, okay? And so therefore, the dots that we do accept follow the desired distribution. Okay, I'll go ahead and give you your first two answers, which are D and B, dog and bear. First answer is D, D as in dog. Second answer is B, B as in bear. D and B. Okay. So I don't know. You can play around with the scripts that I've provided, which is just gives you the PDF of the target distribution, PDF of the proposal distribution. Okay, and then runs the code for the animation. Okay, so there's a package animation that allows you to kind of basically you just generate a whole bunch of plots, and it saves each plot as a frame, and then it will stitch them together into some kind of file. I don't know why the computer keeps beeping. Okay. So if you take a look at some of the details here, this is a histogram. So this is, I generated 100,000 values, okay? And if I create a histogram of the proposed x values, okay, which are coming from the exponential distribution, because we're generating from the exponential distribution, the resulting histogram looks very much like the exponential distribution. Okay, so if we generate values from the exponential, when we plot a histogram of them, these are the random values that we've generated. Okay, so again, it's random, so it doesn't fit perfectly. Okay, so like this one just peaks a tiny bit over the PDF, but overall, there's very close fit between the random values that I've generated or proposed and the PDF of the proposal distribution, G of x, okay? But the issue is that these are not the values that we want to keep, okay? So the values that we want should follow this red line, okay? Now, if I just kind of use this directly, right? And if I just use the exponential values directly and compare them to the PDF of the normal distribution, I could just do, if I didn't use the acceptance ratio, but I just did F is, if F is less than G, okay, like over here, if F is less than G, we throw those values away, then what would happen is the resulting distribution is there's going to be certain segments, like right between here and here, between, I don't know, 0.5-ish and 1.5-ish, where I don't have enough values generated because the exponential distribution is not proposing enough of these values. So I might end up throwing away these values where I say, anywhere where the proposal distribution G is greater than F, we'll accept only some of them, okay? We might throw away some of these things, but we won't have enough values here, okay? And so that's why we have to scale up or scale down, okay? Either scale up the proposal distribution, M times G, so it's going to be greater than F, or conversely, you can do F divided by M, okay? So it fits under, all right? So when you scale up the proposal distribution G, okay, now it fits the entire PDF of what you want, F, fits underneath M times G, okay, or you can also think of this as the PDF of F divided by M, okay, fits underneath G, okay, and so we could look at just kind of this one segment right here for values between, say, 0 and 0.1. And we can see when you look at this, the exponential distribution proposes too many values between 0 and 0.1, whereas the normal distribution or folded normal distribution doesn't generate as many of those values. And so we want to accept only some of them. We don't want to reject all of them, but we also don't want to accept all of them. And so the ratio in which we're going to accept is, we look at how much is below the red line versus how much of the entire thing is there, and I don't know, that looks around 70%-ish or something, okay? So I'm going to basically spin a value between 0 and 1 using the random uniform. If it's below 70%, we will accept it, and if it's above that, we reject it, okay? Okay, so for that first bar, a value of around 0.05, we're only going to accept around 63% of them, okay? So if I calculate, the PDF of the target distribution, PDF of the normal divided by 1.32 times the PDF of the exponential, we say we're going to accept around 63% of them, and then we generate a random U value, right? So how are we supposed to accept only 63%? We'll generate a random U. If that U is less than 63%, we'll accept it, and if it's greater than that, we will reject it. And so we follow that process, and and we do that throughout. Okay, over here, like if you just look at this this bar between 1.4 and 1.5, okay, the acceptance ratio here is going to be a lot higher, around 90%. We're going to accept around 90% of the values. If you do a calculation of f at say 1.45 divided by m times g at 1.45. The f is around 0.279. That's the height of the red bar, whereas the height of the m times g is around 0.31. Okay, so the blue line is a little bit taller than the red line, but only a little bit. Okay, the red line is around 90% the height of the blue line, so we want to accept around 90% of the values that get proposed here. And so we'll generate a random U. If that U is less than 90%, we'll accept it, and then U will be less than 90% of the time. And so we do that, and again, the resulting distribution after this is, I think, 1,000 dots here or something, looks a lot like this. And we keep those under the dots in black under the red line. We've proposed all of these dots under the blue line, but we throw some of them away, okay? And so thus the resulting distribution that we keep follows the target distribution that we want, okay? And so the total kind of acceptance ratio that I get is around 75%. I proposed a certain amount, and that's what we have. Okay. Just to kind of show that this works a little bit with something a tiny bit more mathematical, okay? What we want to show is that when you follow this process, okay, that the probability of getting X is equal to the PDF, okay, that the desired PDF. So we want to show that we're going to generate values according to G. We're going to follow this process and accept only some of them. So therefore, the probability of getting X, assuming that X is accepted or given that X is accepted, follows the target distribution of F. That's what we want to show, okay? And if we can show this, then this would be, this will show that that this process does indeed generate values from the desired distribution, okay? And so, so this is how we'll go about it, okay? So we're going to use Bayes' rule, right? And so with Bayes' rule, we're going to say the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So this is the probability of A given B. So we want to say, okay, what is the probability of, what we want is the probability of getting X, okay, if X is accepted. So this is going to be, what is the probability that X is accepted given that we've generated a particular value of X, okay? And we have to multiply that by the prior probability of just generating that value of X, okay? and then we will divide by the probability that x is accepted. So this is just applying Bayes' rule here. So this part, what's the probability of generating the value of x? Okay, this is coming from our proposal distribution. We're going to generate values, that particular value of x is going to be the PDF of our proposal distribution, which is g. Okay, and then the probability that we're going to accept it is going to be the probability that u is less than our acceptance ratio, okay, which is r. Okay, and the probability that u is less than our acceptance ratio is just going to be the acceptance ratio because u is between 0 and 1, so we can just write the acceptance ratio, which is calculated by doing f divided by m times g of x. Okay, so this part over here is going to be f divided by m times g of x times g of x over here. And then the bottom, the probability that x is accepted, regardless of x value, okay, the probability that we're going to accept this is going to just be the integral of the numerator across all of the possible values of x. Okay, what is the integral of the numerator across all possible values of x? All right, so looking at this, the g of x and the denominator and the g of x here is going to cancel, so the numerator ends up being f divided by m, okay? So that's fine, right? And then if you look at this, here I'm going to just get the integral across all possible values of x of basically f divided by m. G times e. So these g's will cancel. We're going to get the integral of f over m. The integral of f, because f is a PDF, is going to be 1. Okay, and I can use this domain of x, and because the support of f is fully contained within the support of g, I know that this will integrate to 1. Okay, so if again, this hinges on the fact that the support of f is fully contained within the support of g. If it's not, then the integral across the support of g, the integral of f across the support of g will not integrate to 1, okay, because there will be certain values that are missing. Okay, but if the support of f is fully contained within the support of g, then integrating across here, this is technically the support of g, but integrating across the support of g of f will integrate to 1 because it's a PDF. So then you get 1 over m, and then so you have f of x over m divided by 1 over m, and that's going to result in f of x. And so, so this is to show that following this process of using this as our kind of our acceptance ratio and generating a random value of u to decide whether or not to accept it will indeed produce values according to the desired distribution of f of x. Okay. Don't get rejection sampling and importance sampling mixed up. They are similar, but their end purposes are different. Okay. They're similar in that both of them are these kind of workarounds for when you can't generate values from f, okay? But the key here is that rejection sampling is used to generate a random sample itself. So if you need values that come from a given distribution, you would use rejection sampling, okay? If you don't need the actual values, but you just want to estimate some kind of integral or something, estimate the expected value of a function, all right, which is basically what we did Monte Carlo integration for, okay, then you can use importance sampling, okay? Rejection sampling will end up throwing away some of your values, so you will generate a bunch of values and you throw some of them away. That's the rejection part, okay? We throw some of these values away. Whereas importance sampling doesn't actually throw any of the values away. You generate a bunch of values from G, and if you're generating kind of too many of them, rather than throwing away some of them, you just kind of weight them less, okay? You give them a lower weight. You calculate that weight, which is, very similar to kind of the accept or reject, the acceptance ratio, R of x, but we weight them, and so values that get created too frequently get weighted less. Values that are not created enough get weighted heavier, and that's That's what importance sampling does. Okay, we'll go ahead and wrap things up here. Just end a couple minutes early. Let me go ahead and give you your last view quiz answer.